Welcome back, everyone. We're going to talk about hypothesis testing again, but this time for proportions. We've already talked about for the mean, first of all, when the standard deviation was known for the population, and then when it wasn't known for the population. Now we're talking about proportions. The good part is we're going to use a z-test here, just as we did in section 7.12 when we were talking about having the standard deviation of the mean known. That said, there's very little that's different. The main thing is that the test statistic is different. You might see some similarities, but it is different. So take good notes. All right, here we are in chapter 7, and you can see we're about 3/4 of the way through. And this is what we need. We're going to use the z-test, as I just mentioned. That's good news because you've done it previously, except that we're going to use it on a population proportion. And we're going to perform a statistical test on that proportion. But make sure that you check your sample size. Where's my cursor? Here we go. Check the sample size, multiply it times the proportion that you think it is. Make sure that product is greater than or equal to 5. Not only that, but NQ is greater than or equal to 5. Now, in case you've forgotten, Q is just 1 minus P. It's the proportion for whatever it is not happening. The test statistic looks like this. So the population proportion is P. Where's my cursor? There we go. The population proportion is P, and the test statistic is P hat. And this is how you calculate the standardized test statistic. You might recognize some similarities. You might recognize some similarities in calculating z values before. Before you had something like x bar minus mu over the standard deviation, or the standard deviation divided by the square root of n. Notice that you've got the test statistic here, you've got the value you're comparing it against here, and down below you still got that n under a square root. So there's a lot of similarities here, but you have to write this in your notes so that when you're getting the test statistic, you calculate it the right way. All right, in steps. First of all, make sure the distribution is normal. And you can tell it's going to be normal because NP is greater than or equal to 5, and NQ is greater than or equal to 5. State that claim. Mathematically, state its opposite. And the one with the equals, of course, will be the null hypothesis, and the remaining one, the alternative hypothesis. Before you actually find or do your testing, your collecting of data, specify the level of significance represented by alpha is the level of significance. Determine the critical value. Now, you don't necessarily have to use table 4. You can use your technology, and I would suggest you did do that. And we'll have some references to that, and you can always ask in class as well. Once you've got that critical value, determine what the rejection region or regions are, depending on the test. It might be left-tailed, right-tailed, or two-tailed. It's very similar. Find the standardized test statistic. That's the one we just mentioned. There's our sample value. Here's the value we're comparing it against. P is the proportion, same as up here. Q is 1 minus P. And remember, this is divided by n, the sample size, and then square root. Your calculator will do all this for you, though. Once you have that, compare it with the rejection region, and you'll make a decision whether to reject or fail to reject the null hypothesis. If it's in the rejection region, reject H sub 0. Otherwise, fail to reject. Remember, we don't accept it. The wording is we fail to reject it. Once you've decided what you're going to do with the null hypothesis, go back to the claim. What does this say about the claim itself? All right, let's get to an example here so we can play around a little bit. First of all, we've got a claim. The researcher claims that less than 69% of U.S. adults, and that's going to be the proportion. So the claim is that the proportion is less than 69%. You might want to write that, though, as P is less than 0.69. Let's make that P look like a P. There we go. All right, that's the claim. So scratch this off. We don't need it anymore. What's the opposite of the claim? Well, it's greater than or equal to 0.69. Now we get the null and the alternate hypotheses. Which one has equals? The second one. So proportion is greater than or equal to 0.69 will be our null hypothesis, which leaves us with proportion less than 0.69 as our alternate hypothesis. All right, we're ready to go. Also notice that this can be a left-tailed test. In fact, this wouldn't be a bad time to draw a little picture. You're going to have a rejection region in this left tail. Reject region. All right, what do we have for numbers? It says you're going to take a random sample of 100. So n, where's my cursor there? N equals 100. Good. And from that sample, we got a proportion in the sample of 0.65, 65%. And what do we have for alpha? Alpha equals 0.01. Now that means that since we've got a one-tailed test, this area up here is 0.01 of the total area under the curve of 1. All right, what is the rejection region? Well, we have to find the critical value. So what we need is we need to find that Z sub C, as I call it. Where's my cursor? There we go. So what's the critical value? The boundary that we're going to look for. So again, we're looking at Z sub C. So we're looking for we're going to use inverse normal. The area over here is only 0.01, so 0.01. Get that decimal point in there. Since we're talking about a Z value, automatically we have 0 for mean, 1 for standard deviation. And that's going to give us our critical value. And before we actually find it, we'll find that on the next slide. We're going to compare that with our test statistic. We're going to get, where's my cursor again? Okay, here we go. We're going to get our test statistic in time. And if it's less than this critical value, because it's a left-tailed test, then we're going to reject the null. Okay, let's get back to work now. All right, the products. we've got to check this. The 100 times the 0.69, we're good. We're over 5, way over 5. 100 times 0.31, what is the 0.31? Where's my cursor again? There we go. The 0.31 is 1 minus 0.69. Both of those are greater than 5, so we're ready to use a z-test. Here we've got the null hypothesis. Right here, we've got the alternate hypothesis, and label the claim. So when we decide what we're going to do with the null hypothesis, we still have to couch our conclusion or result in terms of the claim itself. It's a left-tailed test, and here is what I call z sub c, or the critical value of z. It's negative 2.33. Remember, our picture showed the left-tailed test out here. So the rejection region is over here on the left side, which means negative 2.33. So the rejection region then is less than that, to the left of that. So if my test statistic is less than that, we'll reject the null hypothesis. But we have to find out what that test statistic really is. This is the value we got from our sample. Subtract that from what we're comparing it against, the 0.69. That goes in the numerator. In the denominator, remember the denominator is PQ over N. There's a P value, there's a Q value, and there's our sample size. Let the calculator do the rest. And our P value, or our Z value, our test statistic, is negative 0.86. Now, what did we say before this? Is our test statistic less than our critical value? Our test statistic is negative 0.86. Is it less than the negative 2.33 that we found for our critical value? No, that's not true. So we're going to fail to reject the null hypothesis. Now, the null hypothesis was not our claim. Since we failed to reject the null hypothesis, we're going to stick with the null hypothesis, which means we don't have evidence to support the claim. And remember, you also mentioned what level of significance you used for this. There. Keep losing the cursor. There we go. That's at the 1% level of significance. Take note again, these are the words you want to use. There's not enough evidence at the 1% level of significance to support the claim that less than 69% of U.S. adults who use live television streaming platforms have upgraded to advertisement-free service tiers. End of story. End of that story. Now, just a reminder, we've done this before, several chapters before. To get that p-hat that we needed, we find it by taking the number of items that was selected out of our sample and change that to a percent, and then change that back to a decimal. That's our sample proportion. X is successes, N is the sample size. You want to try that again? Of course you do. You don't learn something the first time over. All right, first of all, you notice, there's a claim right above. So the researcher claims that 26% of U.S. adults aged 22 to 59, who do not have a parent with a bachelor's degree have completed a bachelor's degree themselves. Well, it says 26% is the proportion. So the claim is P equals 0.26, which means we've also got not equal to 0.26. Which one is the null? That's the null, which means, of course, this one is the alternate. What kind of a test is it going to be? Always look at the alternative hypothesis. It's a two-tailed test. We don't have an inequality pointing one direction or the other. So we've got two rejection regions, one out here and one back here. Now, we had a random sample of 7,400 adults. That's pretty good, right? 7,400 people. And out of those, 1984 said yes. So our p hat for our proportion is 1984 over 7,400. There's our p hat. And we've decided we're going to use an alpha or a level of significance of 0.10 alias 10%. Now we have to check this first because we want to know whether we can use a z-test or not. Well, 7,400 times 0.26, we're way over. And 7,400 times 0.74, that's way over 5 as well. So you can use a z-test. Oops, here we go. You can use a z-test. So we're off and running. So here's our null because it has the equals, just a reminder. And here's the alternative hypothesis. Means it's going to be two-tailed, which means we're going to have two rejection regions. And we can use inverse normal. Let's see, where are we? We can use inverse normal to get the critical value. Now it's a two-tailed test, and our alpha is 0.10, which means we need to use alpha over 2, which is 0.05. Now this is a z critical value, so we'll have 0 and 1 out here. And here we get the two critical values are negative 1.645 and positive 1.645. The rejection regions are less than the negative 1.645 or greater than 1.645. If our test statistic falls in either of those, we're going to reject the null hypothesis. All right, what is the test statistic? Well, our p hat is 0.268. Throw that in our z calculator. Here's the p hat. That's what we got from our sample. We're comparing it against 0.26. Here's our p. Here's our q. There's our sample size. So our test statistic, I'm going to label this as I like to do. It's 1.59. And that is the test statistic. Now remember the areas were 1.645 on this side and negative 1.645 on that side. Where is 1.59? Well, it's here, but it's not in the rejection region. So we're not going to reject the null hypothesis. You can see it. It's close, but it's not in the rejection region. It's just outside the rejection region. So you fail to reject it. not enough evidence to reject the claim. In other words, it's close enough to this middle part that you're going to go along with the claim. All right, that's it, folks. That's hypothesis testing with a proportion. Not too hard, is it? If you really have to admit it, it's not that hard. It's really almost a review of what we did in 7.2 with the population mean when we knew the population standard deviation. Well, folks, we'll see you next time. See if you can give it a shot at standard deviations and variances. It's a little bit different. In fact, you can't use most calculators that way, but I can tell you two different ways of getting it. This is where if any of you have a TI Nspire, you're going to say, yes, I've got the right one. If you don't, then I'll show you an alternate way of using one of the tables, but you'll be in good shape either way. Until next time, take care.